This is an introductory video to section 13.5 related to the tangential and normal components of acceleration and normal components of acceleration. Okay? And just by way of motivation, let me remind you where we've come from. By way of motivation, what we've done in the past is, for example, maybe we've had a vector v given to you as the vector 1, 2. Make this simple by looking at these vectors in 2 dimensions, and let's say the vector w was 0, 3, for example. Okay, so we know that these vectors in the 2-dimensional plane look like the vectors 1, 2, there's v, and 0, 3 is a vector pointing straight up like this. So there would be the vectors v and w. And then the question we would have asked is, maybe you're given a vector a. Okay, maybe you've been given the vector, say, 2, 4. Okay, and then I've asked you to do the decomposition. Take the vector a and write it as some number alpha times v plus some number beta times the vector w. And that would lead you to a system of equations that you had to solve for the numbers alpha and beta. So for example, you would do 2, 4, alpha would be 1, 2, beta is some number we don't know, but the vector w is 0, 3. Okay, and the goal is to use your vector properties, the scalar vector multiplication at this step using scalar vector multiplication. Okay, and then we will add the two vectors together, alpha and then 2 alpha plus 3 beta, right? And that will lead you to your system of equations. 2 has to equal alpha, and 2 alpha plus 3 beta has to equal 4. So this is a nice system of equations because you know alpha already, and if alpha is equal to 2, then that tells you 4 plus 3 beta has to equal 4. Sorry, let me see. So what am I seeing here? So that this says that beta has to equal, okay, I'll just follow this, that beta has to equal 0. Okay, and if beta has to equal to 0, that says that the vector A is equal to 2 times the vector v plus 0 times the vector w. And you probably could have seen that. I just made this example up. I should have thought about it a little bit more. But 2, 4, right? There's the vector A. And what we're seeing here is that the vector A is 2 times the length, 2 times the vector v. 2 steps in the v direction and 0 in the w direction. So this is the kind of problem we've been given. The keys here, the key ideas were that that you've been given two vectors v and w, you've been given some other vector a, and you're trying to write the vector that you've been given as the sum of two other vectors v and w. Okay? And the goal is to find alpha and beta. This is called a decomposition problem. So this leads us into what we'd like to talk about in this video. Okay, the goal is to do this process in section 13.4 in calculus 3. What you're going to be given is some sort of vector valued function, aka a curve in 2D or 3D. Okay, and we're going to find two vectors, the equivalents of the vectors v and w up here. These two vectors that we're going to find are going to be what are called the vectors t and the vectors n. And these vectors, what makes them special is that they depend usually on the time, how you move along the curve, the time. And so these are two vectors that move along with the curve r of t. And I will show you a picture of this in just a second. But this vector t is like the vector v, the vector n is like the vector w. And then we're going to have to find a vector, what I'll call a, like I did above, but the vector a. And this will be the acceleration vector. Okay? And our goal is to take this acceleration vector and write it as a decomposition of the vectors t that you've been given and the vectors n that you found. And so the goal is to find alpha and find beta. Okay? We're verging on physics here, and so these letters alpha and beta, we can actually give them a better name. We'll call them A subscripted with t, which is called the tangential component of acceleration. And the vector and the number beta, we'll call this A sub n, called the normal component of acceleration. Okay? So if we can solve this problem, we will have succeeded in taking the acceleration vector and writing it as a decomposition of the vectors t and n. So this is our goal, and it directly parallels the kind of problem that we've done up here. The only difference is that we have to actually do some work to find the vectors t and n, and we need to then give some physical context to what's going on in this problem. Okay, so I'd like to give some physical context to this problem now by bringing in a picture. Okay, and what we're seeing in this picture is we're seeing a curve. Okay, in this case it's a parabola. Okay, and on the left pane we are seeing the vector t and the vector a. Okay, so on this screen we're seeing the vector on the left. Focus on the left pane. You can see that these vectors change depending on time. Wherever you are on the curve, these vectors are changing. Okay, so no longer will our vectors just be vectors of numbers, but our vectors are going to have the variable time in them because they are changing. So let's take a look at this vector here in red. Okay. What we're seeing here is what's called the velocity vector. It's the vector that points in the direction of the tangent line. So we've talked about tangent lines, so you can see here that this red vector points in the direction of the tangent line. And the blue vector is the second derivative of the curve. Okay, so it's the second derivative of the curve, and that's called your acceleration. Okay. So, if I go to add a page below, okay, what we're seeing on this screen here, okay, I will show you, okay, what we had here was a curve that was given, okay, the curve given was the curve t comma t squared, otherwise known as ti plus t squared j. Okay, and then when you take the derivative of the curve, that's what you get. This derivative of the curve is what we are calling v of t, the velocity vector. Okay, so the interpretation of this v of t is that if you have some curve r of t given, then v of t is the vector or the arrow at the point. Okay, here's the point r of t, and v of t is the arrow at the point r of t that points in the direction of the tangent line. Okay, sometimes this is called or often it's called the velocity vector. Okay. So you pick your favorite time, and because this y entry of the vector changes with time, that the vector will change from point to point. All these right here are examples of the vector v of t. Okay? And then we went ahead and computed, you can compute a second derivative, which is the derivative of the derivative. And this is what we're calling the acceleration vector a. Okay? And notice that its vector is 0, 2, which is why we were seeing in the graph here that this vector, notice that it doesn't have any times in it, in the acceleration vector, and it's always pointing in the y direction, which is what we are seeing here in this picture on the left. Look at the blue vector, and notice that it is always pointing up. It always has a length of 2. So no matter how you move, where you move along that curve, this blue vector, which is the acceleration, is pointing upward. Okay? Now, our goal in this problem is on the right pane. Okay? To create two vectors, okay, to find two new vectors, this solid red one and the solid blue one. Those are our vectors, what we call t and n. T is this red vector. It's the unit tangent vector. That's what it stands for, and it's just the unit vector of your velocity, so it points in the direction of your velocity but has length 1. Okay? And the blue vector n is a vector that's perpendicular to t. So blue is the n vector. Okay? And our goal then is to do exactly what we did in the simple example to start this problem, to take the vector, the acceleration vector, and write it as a decomposition of the vector t and the vector n. So basically we're trying to figure out the acceleration vector, how much of it is pointing in the tangent direction and how much of it is pointing in the normal n direction. Okay? So that's what we can see as an interpretation of the vectors t and n. Let me summarize here on a piece of paper. Okay, so what we need to do next is to talk about the vectors t and n. How do you find them? Okay, the vector t is defined to be the unit vector of your derivative vector, the velocity vector. So to make a unit vector, you just divide the vector by its magnitude. Okay, this is also called the velocity vector divided by the magnitude of the velocity vector. Okay, so if you're asked to find the vector t, okay, all you need to do is to take the velocity vector, which is 1, 2t, and then divide by its magnitude. Okay, but its magnitude is the square root of the dot product of that vector with itself. Okay. So I think we can see here that the unit tangent vector is going to be 1 divided by the square root of 1 plus 4t squared, and then take the second entry and divide by the magnitude, square root of 1 plus 4t squared. This is what is your unit tangent vector. Okay, so now both entries have times in them. Okay, and then the unit normal vector is defined to be, we'll see why it's defined to be this, but the derivative of the unit tangent vector divided by the magnitude of the unit tangent vector. Okay, and I'll leave you to compute. Okay, once you could find those vectors t and n, you will have known the acceleration vector, and your goal is to find the tangential and the normal components of the acceleration, and those tangential and normal components are scalars. Okay, so your goal is to find those scalars. You have found the vector t, you have found the vector n, and then your goal is to solve for at and an. Okay, and there's a convenient little trick here. Okay, and I will write this in bold letters. Note. Okay, very important here. Okay, it still remains to be shown, but if you look on the screen, okay, there's something very important about the vectors t and n. T and n are on this screen right here. Watch that no matter what time you pick, no matter where along the curve you are, at what time, the solid red vector and the solid blue vector, they always stay perpendicular to each other. Okay? That will be true no matter what curve you pick. So for the parabola, t and n look to be perpendicular to each other. If you change the curve, cosine of t, sine of t, let's look at a circle, okay, a new curve, okay, and run this. Here's your velocity, the curve plot. Look here on the right, no matter what time, okay, no matter where you are along the curve, the vectors t is the solid red one, n is the solid blue one, they stay perpendicular to each other, okay? So on a circle, t and n are perpendicular, but also on a parabola, they're perpendicular. So how do we use that perpendicularness? Note that t and n are perpendicular to each other. And you can use this trick, okay, right here. It's not really a trick, it's more a fact. Use the fact, let me make this pen a little bit thicker here. Use the fact that if you dot product both sides of this equation with t, right, then you'll get a acceleration vector dot producted with the t vector will give at, t dotted with t, plus an, n dotted with t. But since t and n are perpendicular, that dot product is 0. And t is a unit vector, so the dot product of t with itself is going to be 1. So now you know, without having to really solve any equations, that the tangential component of acceleration is just the acceleration vector dotted with the unit tangent vector. Okay? And similarly, dotting both sides with the n vector, if you take the acceleration dotted with n, then you'll know the normal component of acceleration. Okay, so that's the trick. Just easy to kind of write down the formulas. It's another thing to actually do some examples because the computations are a little bit messy, even for an example like a simple problem like the parabola. Okay, but these are the basic formulas and the basic idea that you'll need to do these acceleration decomposition problems. Okay. In the next video, I will show you a little bit more about why is it that we know that t and n are perpendicular. I mean, we can see from a picture why that's the case, but it'd be another thing to show it. And then in the next problem, we'll work out a full example on how to do the acceleration decomposition. This video was just to build some intuition for about what the vectors t and n were and what their significance is. Okay, so next video we'll pick up this example.